Wi-Fi technology, based on the IEEE 802.11 standard from 1997, enables high-speed wireless internet and data transfer using radio waves, offering flexibility and mobility by replacing cables with convenient access points, routers, for devices like laptops, phones, and smart TVs. Its development, kicked off by Apple's consumer products in 1999, has evolved rapidly through standards like Wi-Fi 4, 5, 6, and the latest Wi-Fi 7, delivering faster speeds, better range, and increased efficiency for modern applications like streaming and VR. History and evolution. Wi-Fi has evolved through several generations that offer increasing speeds and efficiency. General release max speed standard key features. Year, theoretical, Wi-Fi 1802.11b 1999 11 Mbps first mass market success, 2.4 GHz Wi-Fi 4802.11 N 2009 600 Mbps introduced MIMO, multiple antennas, breakthrough into gigabit speeds, 5 GHz Wi-Fi 5802.11 AC 2013 3.5 Gbps only high efficiency in crowded areas, stadiums, Wi-Fi 6802.11 AX 2019 9.6 Gbps etc. Ultra-fast speeds, uses 6 GHz and MLO Wi-Fi 7802.11b 2024 46 Gbps Tech Core technology and working principles. Radio waves, Wi-Fi uses radio frequencies, primarily in the 2.4 GHz, 5 GHz, and more recently, 6 GHz bands. Access points, APS. A central hub, usually a wireless router, translates wired internet data into radio signals and vice versa. Modulation, to transmit binary data, Wi-Fi uses techniques like orthogonal frequency division multiplexing, OFDM, to split signals into subsignals, reducing interference and boosting speed. Channels, each frequency band is divided into multiple channels, like lanes on a highway. Modern routers often use channel bonding to combine adjacent channels for higher throughput. Key components. SSID, service set identifier, the name of the wireless network. Wireless adapter, a hardware component, internal or USB, that allows a device to communicate with the router. Encryption protocols, essential for security. Modern standards include WPA2 and WPA3 to protect data from unauthorized access. Wi-Fi works as a two-way radio communication between a central network source and various devices, translating digital data into radio waves for air travel and back into data for processing. Key components and their roles. Wireless access point, AP. This is the central hub. Its primary role is to bridge a wired network, from a router or switch, to wireless devices. In homes, the AP is typically built directly into the wireless router. In businesses, dedicated APs are strategically placed to extend coverage and handle hundreds of simultaneous connections. Wireless clients, these are any Wi-Fi-enabled devices such as smartphones, laptops, or smart home gadgets that connect to an AP to access the network. Wireless adapters / NICs, hardware inside client devices that translates ones and zeros into radio signals and vice versa. Radio waves, the invisible cable that carries data across the 2.4 GHz, 5 GHz, or 6 GHz frequency bands. The connection process, step by step. 1. Scanning, discovery. A wireless client sends a probe request or listens for a beacon frame from an AP to find available networks, SSIDs. 2. Authentication and association, the client sends an authentication request to the AP. If credentials, like a password, match, the AP grants permission, and they associate, establishing a formal link. 3. Data exchange, sending data, the client's adapter modulates digital data onto a radio carrier wave and transmits it through its antenna. Receiving data, the AP captures these radio waves, demodulates them back into digital data, and forwards them through a wired Ethernet cable to the router / internet. 4. Security handshake, modern networks use a four-way handshake, example WPA3, to encrypt all following communications, ensuring other devices nearby cannot intercept the data. 5. IP assignment, once connected and secure, the client typically requests an IP address via DHCP so it can be identified and routed on the network. Wi-Fi architecture is structured around the IEEE 802.11 standard, which defines how wireless devices interact at the physical, PHY, and media access control, MAC, layers. As of 2025, modern Wi-Fi architecture increasingly incorporates AI-driven management and support for Wi-Fi 7, 802.11b, to handle massive IoT and high-bandwidth demands. 1. Fundamental hardware components. Station, STA. Any device with a Wi-Fi compliant interface. Endpoints, client devices like smartphones, laptops, and IoT sensors. Access point, APA. Specialized station that bridges wireless traffic to a wired network. Wireless network interface controller, WNIC. The internal or external hardware that allows a station to transmit and receive radio signals. Wireless LAN controller, WLC. In enterprise setups, a central device used to manage multiple lightweight APS, handling configuration, and security policies. 2 logical network structures. Wi-Fi networks are organized into specific service sets. Basic service set, BSS, the basic building block, consisting of an AP and its associated client stations. Independent BSS, IBSS, also known as ad hoc mode, where devices connect directly to each other without an AP. Extended service set, a set of multiple connected BSSs that allow users to roam across a larger area, like a campus, while maintaining a single network identity, SSID. 3 key architectural systems. Distribution system, DS, the medium, usually wired Ethernet, used to interconnect different APS within an S. Portal, a gateway that connects the 802.11 architecture to other types of networks, such as a standard wired LAN or the Internet. Wireless distribution system, WDS, enables the wireless interconnection of APS, often used in mesh networking to extend coverage without additional cables. For 2025 architectural trends. AI-powered networking. Modern architectures now use AI to automatically optimize channel selection, manage power constraints, and proactively detect security threats. Multi-gigabit integration. Due to the 46 Gbps potential of Wi-Fi 7, network backbones are shifting toward 2.5 GBE and 5 GBE switches to prevent bottlenecks. Capacity-centric design. Architecture design in 2025 has moved from prioritizing simple coverage to managing device density, especially for industrial IoT and high-resolution video applications. WDS, wireless distribution system, and mesh networking. A wireless distribution system, WDS, is a technology that enables the interconnection of access points, APS, in an IEEE 802.11 network wirelessly, eliminating the need for a traditional wired Ethernet backbone. Core functionality. WDS allows a wireless network to expand its range by letting multiple APS communicate with each other over the air. In this setup, one AP acts as the main or root station, usually wired to the Internet, while others serve as relay or remote stations to extend coverage. Core functionality. WDS allows a wireless network to expand its range by letting multiple APS communicate with each other over the air. In this setup, one AP acts as the main or root station, usually wired to the Internet, while others serve as relay or remote stations to extend coverage. Key operational modes. Wireless bridging. APS communicate exclusively with each other to connect separate wired LAN segments. In this mode, they typically do not accept connections from end-user wireless devices. Wireless repeating. APS communicate with each other while simultaneously allowing client devices, like phones or laptops, to connect. This is the most common use case for range extension. Advantages and disadvantages. Feature description. MAC. Unlike some other repeating methods, WDS preserves the original client MAC preservation addresses across links, which is critical for seamless roaming and security policies. Reduces the need for expensive cabling in complex environments like warehouses, cost-effective or old buildings. A major drawback, effective bandwidth is typically halved for each wireless hop throughput because single radio APS must use the same channel to receive and then retransmit lost data. Interoperability is often poor between different brands, and sometimes even compatibility different models from the same vendor, because WDS is not fully standardized in the 802.11 specification. WDS versus mesh networking, 2025 context. As of 2025, WDS is considered a legacy or budget-friendly option compared to modern mesh networking. Static versus dynamic. WDS links are usually static and require manual configuration of MAC addresses. Self-healing. Unlike mesh, WDS lacks self-healing capabilities. If one relay node fails, all downstream nodes lose connectivity because there is no automatic alternative path. Multi-hop. WDS typically supports only 2 to 3 hops before performance becomes unusable, whereas mesh can scale to more complex topologies. Mesh networking is a decentralized Wi-Fi architecture that uses multiple interconnected hardware devices, known as nodes, to create a single, unified wireless network. Unlike traditional routers that broadcast from a single point, mesh systems work like a web, allowing data to hop between nodes to find the most efficient path to its destination. Core architecture and components. Main router, gateway, the primary node connected directly to your modem via Ethernet. It manages the entire network and the Internet connection. Node/satellites, additional units placed throughout the area that communicate wirelessly, or via wired backhaul, with the main router and each other. Backhaul, the dedicated communication link used exclusively for nodes to talk to one another, keeping this traffic separate from client device data to maintain high speeds. Single SSID, the entire mesh system uses one network name and password, allowing devices to switch between nodes without losing the connection. Key features and 2025 trends. As of 2025, mesh networking has become a standard for both smart homes and enterprise environments. Self-healing, if one node fails, the network automatically reroutes traffic through other active nodes to prevent downtime. Seamless roaming, using protocols like 802.11k/v/r, Mesh systems automatically hand off your device to the node with the strongest signal as you move, ensuring no interruptions during video calls or gaming. Wi-Fi 7 integration. By 2025, high-end mesh systems like the Eero Pro 7 and TP-Link DAC B series use multi-link operation, MLO, to connect nodes across the 2.4 GHz, 5 GHz, and 6 GHz bands simultaneously, dramatically increasing bandwidth and reducing latency. AI-driven optimization. Modern systems use AI to learn user movement patterns and device distribution, automatically adjusting node connections to provide the best signal. Mesh versus traditional range extenders feature mesh networking. Range extenders network name single SSID, unified, often separate names for each device. Handoff seamless and automatic, often requires manual switching. Speed high, uses dedicated backhaul, significant loss, bandwidth cut by 50%. Reliability self-healing, multiple paths, single point of failure, star topology. For optimal performance in 2025, experts recommend tri-band or quad-band mesh systems to ensure a dedicated frequency is available for the backhaul, preventing network congestion. How IP multicast behaves on Wi-Fi networks. IP multicast on Wi-Fi functions as a bandwidth-saving method to deliver a single data stream to multiple interested receivers simultaneously. However, because Wi-Fi is a shared wireless medium, it handles these transmissions differently than wired Ethernet. 1. The core mechanism. Group management. Devices, clients, use the Internet Group Management Protocol, IGMP, for IPv4 or multicast listener discovery, MLD, for IPv6 to notify the access point, AP, that they want to join a specific multicast group. Layer 2 delivery. Once a client joins, the AP transmits data using a specific multicast MAC address derived from the group's IP address. All subscribed clients listen for this MAC address and process the packets, while non-members ignore them. 2. Wi-Fi specific challenges. Standard IP multicast over Wi-Fi often suffers from performance issues due to the IEEE 802.11 protocol design, unreliability, no ACS. Unlike unicast, one-to-one, traffic, standard multicast frames are not acknowledged, ACT, by recipients. If a packet is lost due to interference, the AP does not know and will not retransmit it, leading to potential packet loss. Lowest common speed. To ensure every device in the area can receive the signal, APs typically transmit multicast at the basic/lowest supported rate. This consumes significant airtime, which can slow down the entire network. Power save mode. If any connected client is in power save mode, the AP buffers multicast traffic and only sends it after a delivery traffic indication message, DTIM, beacon, which can introduce latency. 3. Optimization strategies. 2025 standard practices. To overcome these limitations, modern Wi-Fi networks employ several optimizations. Multicast to unicast conversion. Many modern APs convert multicast streams into multiple unicast streams, one for each client. This allows the AP to use higher data rates and reliable ACS for each device, often improving performance despite the duplicated traffic. IGMP/MLD snooping. Switches and APs snoop on group management messages to maintain a map of which ports or wireless clients actually need the traffic. This prevents the network from flooding multicast data to devices that didn't ask for it. Wi-Fi 7 enhancements. 2025 new Wi-Fi 7, 802.11b, systems use multi-link operation, MLO, to transmit data across multiple frequency bands simultaneously, significantly reducing latency for real-time multicast applications like VR and cloud gaming.